So one more quick little proof that I want to work on. Again, I'm always starting with the highlighter. I love it. I'd now like for you to show that for any natural numbers a, b, and n, with ab equals n, either a is greater than the square root of n or b is greater than the square root of n, and then this is an inclusive or, so I'll just highlight that by saying or both. Okay, let's prove this. Now, first off, this should not be surprising. If I tell you a times b is equal to n, then you would expect that at least one of them is bigger than the square root of n. And just following your intuition should get you close to a proof, okay? So if a times b is n, then one of them should be relatively big. So we're going to do this as a proof by cases. So case 1, and this is going to be a funny way to prove something by cases. Case 1 is what if we're already done? What if a is greater than or equal to root n? Then we're done. And because I've finished a part of the proof, I like to put this little double diagonal line, but you don't have to. But it looks like we're halfway done, right? So case 1 is if a is bigger than the square root of n, bigger than or equal to the square root of n, we're already done. Hooray! Okay, it's a little funny. Case 2, what if a is not greater than or equal to the square root of n? Okay, then we got to work. Grumble. Okay. Well, if a is not greater than or equal to the square root of n, that would imply that a is strictly less than the square root of n. All right? Makes sense? So if a is strictly less than the square root of n, I can multiply both sides by a positive number. I'm just going to write this down. So we know that b is a natural number, which means it's positive. Why am I making a fuss that it's positive? Since b is positive, I don't have to flip this this less than sign. Like if I wasn't sure if b was positive or negative, then I might have to split into further cases where sometimes we have it go one way, sometimes we have it go another way. Whatever, multiply both sides by b, and I get ba is less than square root of n. But guess what? I know something about ba. Ba is equal to n. And guess what? I know that n is equal to the square root of n times the square root of n. Okay? Make sense? We okay so far? Oh, sorry. I multiplied the left-hand side by b. I also need to multiply the right-hand side by b. Okay, I know that that n is equal to the square root of n times square root of n. Well, let me just collect what I've got. Square root of n times the square root of n is less than the square root of n times b. Let's divide both sides by the square root of n, which again, divide both sides, there's a missing e there, by square root of n, which is also positive, because remember, n is a natural number. Now I can cancel these, and I get that n is strictly less than b. Now, I just showed n is strictly less than b. Does that mean that b is greater than or equal to the square root of n? It does. This is actually a stronger statement than this. So we've proved more than we needed to in this case. So root n strictly less than b implies that b is greater than or equal to root n. Here we're actually losing some information, but that's all we needed to show. And that's the end of the proof. So the main idea here was we took all possible cases of natural numbers a, b, and n, where a times b equals n, and we split them up. We split an infinite number of cases, or an infinite number of possibilities, into two different sets. So the two different sets were, one, what if a is bigger than or equal to root n, in which case we're done, because that was one of the things we wanted to show. And case 2 is what if a is not greater than or equal to root n. Well, then we work a little bit. If it's not greater than or equal to root n, that means it's strictly less than root n. Now, I can multiply both sides of this inequality by a positive number, And that's how I get BA is strictly less than root n times B. Now, when I first went through this, I forgot to write that on the right-hand side. Okay, but BA is the same as A times B, which is n. So BA is equal to n, and n is equal to root n times root n. So what we got was root n times root n is strictly less than root n times B. I divide both sides by root n and cancel, and I get root n is strictly less than b. By the way, when I divide both sides by a positive number, I don't have to move the less than sign. It stays less than. It doesn't have a chance of flipping. But this means I've got root n is strictly less than b, and that is even stronger than b being greater than or equal to root n. So I'm